All right, so this is like my favorite section of chapter 2. This is where like we get to do some really cool math. And we get to learn these two cool theorems. So one of them is the polynomial remainder theorem. Have you guys seen this one? So if polynomial f of x is divided by x minus k, then the remainder is r equals f of k. Pretty neat, isn't it? Do you guys understand what that says? Yeah, it's great math jargony stuff. I'm going to show you an example here of what that means. So what I'd like you guys to do to start off is look at part A here. I've given you a function, and I'm asking you to find f of negative 3. Could you please, we're going to use our calculators to do this, but if you were in an Algebra 1 class and I asked you to do this and to show me one step, could you write the one step that you would show me off to the side here, and then go ahead and find a value for me? Find f of negative 3 for this function. Find f of negative 3. You guys know how to do that. The step that I'd be looking for is, are you showing me the function with negative 3 plugged in place of all the x's? And then after that, if you want to jump straight to your calculator, plug those numbers in and get an answer, that's fine. Please do not shout out the answer. No spoilers. I don't want to know what it is. All right, so everybody got an answer? Still working? Okay, don't tell me what the answer is. I'm gonna get you the answer, the same answer, I hope, but I'm gonna do it a different way. You guys ready? Watch this. I'm gonna find f of negative 3 for this polynomial. So I want to plug it negative 3 into the polynomial that has coefficients 1, 3, negative 11, and 2. Does this look familiar to you? Yes? What am I doing? Synthetic division. F of negative 3 is 35. Is that right? Is that what you guys got? Nice. Where did I get that from? It's the remainder. Did you guys know this? So this theorem says, if we read this again kind of more carefully now, let's start at the end. The remainder is f of k. The remainder is f of k. So I asked you to find f of negative 3, so the remainder was f of negative 3. The remainder for what, though? The remainder when we took this polynomial and divided it by x minus k. So I just divided this thing by x minus negative 3, aka x plus 3. And my remainder here ends up being exactly what I would have gotten if I had plugged negative 3 into the function. So we used to use this a lot back before calculators because it was way faster to plug numbers into a polynomial this way than it was to try and do it out by hand. So that's kind of handy. All right, I'm going to let you guys do this in a second on your own, but let's talk about B and C here. What is the remainder when f of x is divided by x plus 3? Okay, we just found that it's 35. Just write down 35. You don't need to copy my work. You're going to do one on your own here in a second. And I think you guys probably know the answer to this, but let's just make sure. Based on that remainder, is x plus 3 a factor of our polynomial? Yes? No? I'm seeing a little bit of both. Anybody want to justify their answer? No, you don't want to justify your answer, or no, you're adamant that your answer is no? The answer is no. Why? How do I know it's not a factor? Because the remainder is not 0. Okay, so if the remainder is 0, that means it divides in evenly. If there's a remainder, that means it didn't go in evenly. So no, because the remainder is not equal to 0. That's what the second theorem says. It says a polynomial function has a factor x minus k if and only if f of k equals 0. In other words, it's only a factor if you can divide it and get a remainder of 0. So we just divided. We did not get a remainder of 0. Therefore, it's not a factor. So I would like for you guys to use this same process to please find me f of 2. So instead of plugging 2 into your function, can you please use synthetic division with the same polynomial function to find me f of 2? So you're going to have a 2 in the box this time. Ooh. You guys coming up with 0? Aha, so f of 2 is 0. That means the remainder is 0, which means, is it a factor? Yes or no? Yes. Yes, how do we know? Because the remainder is equal to 0. All right, this last question here is one of the more important ones that we're going to talk about today. Can you please write me an equivalent form of f of x? So here's one form of f of x up here. Can you write me a different equation for f of x? It would be the same function, but has the x minus 2 factored out of it. What would the other factor be once we have factored out the x minus 2? Does somebody want to be bold and tell me what you think that other factor would be? What do you think? That's it. Nailed it. X squared plus 5x minus 1. Do you see where we're getting that from? All right. So we're going to be doing a lot of synthetic division today, but I want you to keep in mind why we're doing the synthetic division and what our results give us. So one of the things that I need you to know is when we do synthetic division, we can use it to check and see if that thing that we divided out, and just to remind you, we divided x minus 2 out of that polynomial. We can check to see if this thing is a factor of our polynomial. We'll know that because of the remainder being 0. But more than that, the quotient that we get as a result of dividing it out when the remainder is equal to 0, that gives us our other factor. Okay, we feeling okay about that? Let's move on. Oh, P over Q list. Do you guys remember these? The rational zeros theorem. A lot of the other books that I've used call this the rational roots theorem, but kind of the same idea. This was that list. You guys remember, I was just talking about how you may remember last year kind of hunting and trying to do a bunch of synthetic division. You're going through a list. Sometimes you got lucky and you found something early. This is how we generated that list. Do you guys remember how to find that list? We need some p-values and some q-values. Let me remind you. The p-values are going to come from your constant term. We ignore the sign on this when we do it. And they are all of the factors of that constant term. So my constant term is negative 4, but I'm just going to think about the 4, and I'm going to think about what integer factors do I have for the number 4. It'll be 1 and 2 and 4. And then the q list is the same idea, but this time it's all the integer factors of your lead coefficient. Again, ignore your sign. So I'm looking at that 6. Factors would be 1, 2, 3 is a factor of 6, and so is 6. That's my q list. So we make a p list, we make a q list, and then what do we do with it? We make fractions out of those. We make all of the fractions that we could possibly make with one of these numbers on the top and one of these numbers on the bottom. All right, some of these are going to be redundant because they're going to be equal to each other. For example, we're going to get 1 over 1 and 2 over 2, which both have the same value. But how many different fractions could we make with these 3 numbers and these 4 numbers? How many different fractions are we going to have? 12. 5, 6, 7, 8, 9, 10, 11, 12. This is a really tedious part of this lesson. So we're going to go through and make fractions for these. And if you do this kind of in an organized way, it's not so bad. I'll show you my favorite way of doing it. So these Q numbers are going to go on the bottom. So I'm going to go 1, 2, 3, 6, 1, 2, 3, 6, 1, 2, 3, 6. And then my Q numbers, I'm going to go, green pen go 1, 1, 1, 1, 2, 2, 2, 2, 4, 4, 4, 4. I've seen people do this kind of using a table too, and that works fine. So those are all our fractions. Now, of course, we can have positive and negative versions of these. What we're going to do now is we're going to list those in ascending order. So from least to greatest. And we're going to put plus or minuses in front of each of them. And we're going to check for redundancies while we do this. So let's list them out in ascending order. So here's our list. So look through there and tell me what's the smallest value you see in that list. 1/6, agreed. So plus or minus 1/6. And I like to check these off as I go. Are there any other fractions that are also equal to 1/6 in that list? I don't see any. Next biggest. 1/3. Plus or minus 1/3. Check. Is 1/3 anywhere else in that list? 2/6. Yeah, so we can check that off. We don't need to include that. It's already in our list. Okay, I think next would be a half. Yeah, plus or minus a half. So here's my half, and I think I've got another half over here someplace. Oh, maybe not. No, nothing else reduces to a half. Is 1 next? Anything else less than 1? Oh, 2/3. 2/3. Bless you. 2/3. And 2/3 is also 4/6 is also 2/3. Now I think it's 1, which I've got there and there. And then anything, 4/3 would come before 2, wouldn't it? 4/3 next. And then 2. And then, oh, here's 4/2 is also 2, and then 4. Do you guys remember doing this? It's kind of tedious, not terribly difficult. What's much more important, though, is why do we do this? What is special about this list of numbers? These are the potential rational zeros for this function, potential rational zeros. So let me ask you guys a couple questions. 3 possibilities, yes, no, or maybe, okay? Is 3 a 0 of this function? Is 3 a 0 of this function? Yes, no, or maybe? No, absolutely not. It's not. It's definitely not, because it's not on the list. If it was, then it would have to be on our list someplace. Okay? Is 4 a 0 of this function? Maybe. It's on the list, so it could be, but we're not guaranteed for sure that it is. How about -6? -6, definitely not a 0 because it's not on our list. All right, here's a tricky one. How about the square root of 5? Yes, no, or maybe? Is the square root of 5 a 0 of this function? Is the square root of 5 rational? Can it be expressed as a fraction or a non-repeating decimal? It cannot. So the square root of 5 is not rational, so it really doesn't have anything to do with this list. It could be a 0, but maybe not. So we can't rule it out just because it's not on this list, because this list only gives us a list of possible rational roots. Okay, things that can be expressed as fractions. Okay, again, your good news is last year you might have been used to like going through that list and like plugging them one by one using synthetic division to see if you get a remainder of 0. We're not going to do that this year. We're going to use our calculator. So make sure you got those handy, and we'll flip over to the next page and do our first example. All right, again, I got a step-by-step list up here. I'm not going to go through and read all this stuff to you. I'm just going to take you through, but I need you to keep in mind, even though this is a step-by-step process, it is important that you understand what we are doing in each of the steps and why we're doing it, because it's not always going to be like this. We're going to add some wrinkles in as we go into our later sections in this chapter. So you'll be using a lot of these same tools, but you're going to have to use them in different ways. Okay, so you cannot just memorize your way through this process. You really need to understand what's going on at each step. So I'll ask you some kind of guiding questions to help us digest that as we're going. Okay, so let's do this. Get this stuff out of the way. First of all, I want to give you a little spoiler of something that's going to be coming up called the fundamental theorem of algebra. But basically it says if you've got a 4th degree polynomial, then you can expect to have 4 zeros. Okay, now some of those zeros might be repeated. Like if there's a multiplicity 2, that's going to count twice. But we're going to have 4 zeros for this thing. Okay, absolutely, we'll have 4 zeros. So part of our goal in this problem is to find the zeros. So let's go ahead and start setting it up. We know that we're going to have 4 zeros. All right. So how are we going to find those zeros? Well, we could make a P over Q list and start hunting through them. But again, this year we're not going to do that because we've got these fancy graphing calculators and they can give us some hints about some zeros that we should be checking. So let's jump straight to our calculator right now. I'd like you to type that function in. So go into y equals, get that function typed in. Graph it. Make sure you're on your standard zoom window. So when you go to graph, just hit zoom standard, zoom 6. That'll default back to your standard zoom window. Our goal right now is to find some zeros. Where will we be looking on our graph to find zeros? The x-axis. Zeros correspond to x-intercepts. So hopefully when we graph this thing, we're seeing some x-intercepts. We might have as many as 4, but we could have less. Ooh, we have less. Is anybody disappointed that we have less than 4 x-intercepts? Are we still okay with that? What's special about this x-intercept right here? It bounces, which means it's a multiplicity of 2. So 2 of these are going to be an identical number. I'm just going to list them twice rather than saying it has a multiplicity of 2. So looking at that, give me a guesstimate. What does it seem like? Can you kind of eyeball and see where that is? What would be your best guess? -3. Are we certain it's -3? Could it be like -3.1 and our calculator just isn't sharp enough to show that difference? It could be. So let me show you. This is a new function on the calculator for some of you, and we'll be using this a lot. This is under the calculate menu, the same place where you find your maximum and minimum and 0. Do you guys remember how to get there? Second trace. And it's the one right up at the top. It's actually the one that gets used the most, so they put it up at the top. It's this value. And if you hit that button, hit enter on that, it's going to take you back to your graph with a cursor after x equals. They're asking you for an x value. When you type in your x value, your calculator is going to take that x value, stick it into the function that's in y1, and spit out the y value that goes along with it. So I'm going to type in -3. What am I hoping to get back for my y value? If it is truly a 0, I should get 0 back, and yes, I'm not disappointed. It is -3. So I got -3 from my graph. What about this one where it's bouncing? What do you think? Does it seem like -1? Can you guys please verify that for me using that second calc value function once more? It will ask you for an x. Try -1 and make sure we're getting 0 back for that. Yes. So -1. And I'm actually including it twice in my list. Because why again? Because we're bouncing off there. We know it's a multiplicity of 2. All right. Now, we could try to guess and check and find this other one here, but I'm going to tell you it's not going to be a nice integer answer, or 0. Somewhere between 0 and 1. So there is a quicker way to find this than the path I'm going to take you on right now, but I want you guys to follow along with this for me, okay? And then we'll come back and talk about the faster way. So here's what I propose we do. We know that we have 3 factors already that would divide into this polynomial. What we're going to do is we're going to use division to start dividing these factors out. Okay? This is a factor of x plus 3. And then we've got 2 factors of x plus 1. Do you guys have a preference which one we do first? Do you want to do the 1s first, or you want to do the 3 first? We're going to end up doing all of them. 3 first sounds good. All right. So we're going to divide out that -3 and write kind of small because we got a little chunk of work to fit in here. Bring out that -3, and we're factoring it. We're dividing it out of 5x to the 4th plus 22x to the 3rd plus 20x minus 6 minus 9. And we're going to do our synthetic division. And can you predict before you get started anything about the result of this synthetic division? What are we expecting to see in this spot once we get done? We better be seeing a 0. If we don't, that means that this thing isn't actually a 0. So go and do your synthetic division, and it's okay as you get closer to that remainder box. If you start seeing the 0 come up and you get a little excited about it, it's okay. It is pretty thrilling. All right, 5, -15. What is that? 7, -21. There's -1. This would be 3. -3. Oh, it's gonna work. It's gonna work. Yes. Nice. Nice. All right. Okay. Now, what did we just do? We just took our polynomial and we divided it by something. What do we divide it by? X plus 3. When we divide stuff, we're actually factoring stuff out too. Right underneath this, I'd like you to rate me another version of this polynomial function. One that has a factor of x plus 3 sitting out in front. What would the other factor be that would come after that? You guys got it. Good, good. That would be our quotient. Now, most of the time, I would not be writing this down, but I want to make sure we're making a connection between what we're doing and why we're doing it. What we're starting to do is we're taking this polynomial and we're going to pull it apart into its smaller factors. Every time we pull a small piece off, the piece that's left over gets a little bit smaller. So we're going to continue to divide out some more factors. The next one I'm going to do is this first x plus 1. But when I divide this off, I'm not going to divide it. I'm not going back to my original polynomial anymore. I'm going to go back to this little leftover chunk that's here. And let's factor that x plus 1 out of this thing. Okay? So I'm just going to add it right on to my synthetic division. These are the coefficients for the leftover piece, my quotient. And this time I'm going to divide out x plus 1. So we would need a -1 there. And I'll go ahead and do my synthetic division for this. And again, we should get a remainder of 0. If we don't, the -1 is not a factor. Yes. Yes. Once you get that divided, could you write me a third version of this polynomial? What did we just divide off? X plus 1. What's left over after we do that? All right. We've got one more factor that we know for sure. We've got another x plus 1. Since it existed twice, that means we should be able to divide it out twice. So go ahead and take that last piece that you got, and let's divide out another x plus 1. So again, that would be a negative 1 in that box. Nice. All right, and then go ahead and write down our final version here. All right, I'm waiting for a couple questions. Someone asked some questions. Yes? Great question. How do we find that fourth zero? So the first zero came from this factor, and the second one and the third one came from these factors. So where are we going to find the fourth one? From this factor. So what's it going to be? You got it. Nice. What a great timed question. Perfect. You read my mind. Are we okay where that 3/5 came from? All right, I'm waiting for a couple other questions. Did anybody write this as x plus 1 with a square on it instead of writing it out twice? Okay. And that's fine. That's fine. That's probably how I would normally write it, but just trying to be consistent here. I got a question for you. Don't write this down. Just look up here. Would this be a viable factoring as well? I'm going to go ahead and square it this time. X minus 3/5. So it's basically the same thing, but I've changed the format of the last factor. Is this going to give me the same 0 that this one would? Yes, so this works as it is. Almost. There's actually a small problem with this that we would need to fix if we were going to write it this way. Can anybody spot the small problem? So multiplicity of, say that again. Yes, the 5 is the issue. Is it this 5 that you're talking about? You're talking about a different 5. Okay, I appreciate your honesty. This is the 5 that I was looking at. What do we want? We want our lead term. If we were going to multiply this thing out, it should end up being 5x to the 4th. The first term should be, right? In the original one, I think we would accomplish that because we got x times x times x times 5x. That is 5x to the 4th, right? Do you see how this is not going to get us 5x to the 4th? We got x times x times x times x. We're just going to get x to the 4th. But we could fix that by simply doing what? Stick a 5 out in front. So sometimes when you do these factorings, depending on how you choose to represent If you've got a 0 that's a fraction, depending on how you choose to represent that factor, you may need to stick a coefficient out in front because of that. So, and I often forget to do this. I try and remind myself, like, when I'm done with the problem, just make sure you're still going to get the right first term here. Make sure if there's something else we need to multiply. Let's do it. Okay. Let's go on to the next one, and then we'll come back and talk about how we could have made this process a little bit easier for ourselves. Okay. Same thing. Same thing. Let's start by graphing it. How many zeros are you expecting this time around? I expect 4 also. Go ahead and get that set up. And let's graph this thing and see what it looks like. Hopefully we'll get some good x-intercepts. All right, fingers crossed for some good x-intercepts here. I don't like that one, or that one, or that one. I like that last one. That last one looks like it might be friendly. As I look at my x-intercepts from left to right, do you see why I'm not super happy about the first 3 of them? Because they're kind of in between. That's okay, we'll deal with that in a moment. But this last one looks like it might be at, is it 3? Can you guys verify that there is a 0 at 3? Second calc value, 3. Yes, all right, so we found one of them. That's good. So that one came from our graph. And then we've got some others too. So let's see if we can leverage some of the stuff that we already know. So one thing that could be potentially useful to us right now is to make a P over Q list. So let's go ahead and do that. And this is not super mathematical of me, but this is how I do this. When I'm using a P over Q list for a problem like this, I write P over Q, and I draw a big fraction bar, and I just list all the factors on the top and list them all on the bottom. And then I just kind of mentally make fractions out of them. So factors of 30 would go on the top. That's 1 and 2. 3 goes into 30. 4 does not. 5 does. 6 does. 7, 8, 9, 10 does. 15 does. Ooh, that's a lot of factors. Thank goodness we're not actually listing these out this time. And then my Q list is much shorter. Factors of 3, that's just 1 and 3. All right. So here's what I'm thinking. What I know from my graph, I can see that I have a 0. I've got 3 others that I need to find. One of them is between 0 and 1. One of my x-intercepts I can see right here on my graph. Somewhere between 0 and 1, I got an x-intercept. So I want you to look at our P over Q list and see if you can find me any fractions that we can make out of these different options that would be bigger than 0 but less than 1. 2/3 is an option. Any others? 1/3 is an option. Any others? I think everything else is either going to be 1 or bigger than 1, right? Okay, so let's use our calculator to check and see whether 2/3 or 1/3 is an option. That second calc value, you can put fractions into that. Just use division. So second calc value, it'll ask you for an x value. I'm going to try 1/3 first. I'm just typing it as 1 over 3. And, bummer. I didn't get what I wanted. I didn't get a y value of 0. So 1/3 is out. Hopefully 2/3 will work for us. I'm seeing some signs of positivity from the crowd here, so feeling pretty good. Yes, yes, okay, found it. So we found that one. So 2/3 is also one of our zeros. Cool, 2 down, 2 to go. We feeling good? All right, what else we got? There's another one between 1 and 2, it looks like. So look at that P over Q list and see if you can make me any fractions that would fall between 1 and 2. 5 over 3 is the only one I'm seeing. Does 5 over 3 work? Oh, please, please work. Yes? No? Oh! No. It doesn't work. Bummer. Well, we got one more we might be able to find here. Let's see if we can find this one over here. That looks like it's somewhere between -4 and -3. Which fractions can we make that are, it needs to be bigger than 3, less than 4. 6 over 3 is 2. 10 over 3 is 3 1/3. Oh, that would work. 10 over 3, maybe? It's in the right area. It would be -10 over 3, though, right? Because we said between -3 and -4. All right, come on, work for us here, please. Drum roll. Wah, wah, wah. Nope. Didn't work. Sad face. All right. So what do we know? We've got 2 zeros. One of them's between 1 and 2. One's between -4 and -3. What do we know about those 2 zeros? They're not rational. The only possible rational numbers we tried and they didn't work. So these must be irrational. Yay! We like irrational things because it's going to give us an opportunity to practice some fun stuff. Irrational probably means it's going to have a square root or something in it. Maybe a pi. Probably not pi. So how are we going to find them? Well, we can get a decimal approximation, but we want an exact value. We want an exact value. Suggestions? What do you think? The thing where we, oh, these, like the synthetic division part? No, what were you saying? What were you thinking? Oh, in the calculator? The second calc 0? Well, and we could, if we were looking for a decimal and we were okay with something that's accurate to like the 10,000th, then that would be totally fine. But if we wanted an exact value, which is usually what they want in math, what else could we do? What do you think? Yes. Okay. So I want you to look into the crystal ball. Look into the future here, okay? Nailed it. Nice job. So we have these two zeros, which means we have 2 factors. We've got x minus 3, and we've got x minus 2/3. If we took our big old polynomial here and we started pulling those pieces off, right? So if I divide out that x minus 3 and keep that separate, and then I take that little smaller chunk and I pull off the x minus 2/3, what are we going to be left with? We're starting with a 4th degree polynomial and we're dividing 2 linear factors off of it. What's that chunk, that leftover chunk's going to be what degree? 2nd degree? And that's good, that's a quadratic. We got all kinds of tools we can use for quadratics, right? We know how to factor those. We know how to do completing the square. We know how to do quadratic formula. So I think that's going to be our best path. So let's do it. Let's do it. So which one would you like to divide out first? The easier one or the more difficult one? Please say the 3. Yes? Yep. Yes, of course. Remember, it gets shorter each time, so save the more challenging things for the end, right? All right, so let's do this 3 first. We're going to divide that out of our polynomial here. So 3, negative 5, negative 31, 67, negative 30. And I want you to keep in mind what we're doing here. When we do this, we are dividing by x minus 3. We're factoring out that x minus 3. We're going to see what that chunk is left when we do that. And I'm hoping for a 0 here. Let's see if it works. Oof, negative 19, I think. 60, but not quite 60, 57. 57. That's 10. Yes, it's going to work. It's going to work. So we took our original polynomial, we factored out an x minus 3. Now we've got this smaller polynomial. This guy's called the depressed polynomial, by the way. It's smaller. So here's our depressed polynomial. We can depress it even further by dividing out anything else that we know, which we do. We got 2/3 here. Let's divide that out too. So now I'm going to divide this polynomial by x minus 2/3. And you guys remember the whole shortcut when you're doing fractions here, right? Divide by the bottom first and then multiply by the top. Divided by 3 is 1 times 2 is 2, 6. 2/3 of 6 is 4. 15. 2/3 of negative 15 is negative 10, and 0. Yes. All right, you guys are doing awesome. I'll pause here for a moment and make sure that folks are caught up. So what did we just do? I like to think about this as it's like a big ball of pizza dough. And we're pulling little chunks off of it. We're trying to portion it out. Smaller and smaller factors. We pulled this chunk out, that made it a little smaller. We pulled this chunk out, that made it a little smaller. Now we want to try and split this thing up into a couple of factors. That'll give us our last 2 zeros. All right, let's go ahead and write out the factored version of this that we know so far. We're actually going to put it in this spot right here. So this is f of x equals, leave a little space here because we might need a number in front of our first factor. Bless you. I'm not sure yet until we get this written down, but let's write the factors that we know. We had an x minus 3, we had an x minus 2/3, and then our final factor was 3x squared plus 6x minus 15. And once you get that written down, can you compare that to the original polynomial? Look at the lead term here. And make sure that if we were to multiply this out, are we going to get the lead term that we're looking for? We would have x times 3x squared. That's going to get us the 3x to the 4th that we need. So do we need anything extra out front? No? Okay. Just for fun, if I had written this way instead, x minus 3, if I had written this as 3x minus 2, which would also have the same 0, and 3x squared plus 6x minus 15, that would be another way that I could write this factorization. Would I need to put anything out front for this? what would my lead coefficient be? We want it to be 3x to the fourth. Is it going to still be 3x to the fourth? I'm seeing 9x to the fourth. So what would I need to put out front for this one to make it work out? 1/3. I would guess if you were to look in the back of the textbook for this problem, for a similar problem like this, they probably would write it out this way. I'm just showing you guys these different formats because they are all correct. So if you're doing a problem and you look in the back of the textbook, I don't want you to freak out if you see something that looks a little bit different from yours. So I just divided each of these coefficients by 3. That's not going to change zeros. All I'm doing is shrinking this thing. And I would not need anything out front here, I don't think. Right. Okay. So to find our last two zeros, we're going to have to deal with this quadratic. We've got 3x squared plus 6x minus 15. And how do we find zeros for anything? We set it equal to 0, and we solve. So we got a few options here. We could use factoring, we could use quadratic formula, we could use completing the square. Would this thing factor? No, you know for sure it's not going to factor. Is that because you've tried, or do you have some other indication that this would not factor? You tried. Okay, I love it. Without trying, can we save ourselves the hassle of trying something that we know is not going to work? I'm going to tell you that this would not factor. I wouldn't bother trying. If it did factor, it's going to factor into something like 2x minus 1, which you should be able to set equal to 0 and get a rational 0, right? But is this going to have any rational zeros? We already know that these zeros are going to be irrational, which means this thing is not going to factor. So don't bother. So that leaves us with completing the square quadratic formula. What do you guys want to go with? Quadratic formula. Let's do it. Let's practice it. Anything that could make our lives easier? What could we do to make our lives easier? We could take out a 3. We could divide by 3, or we could factor a 3 out. That's an equation, so we're allowed to divide everything by 3. That's going to get us some smaller numbers to deal with. I am going to have you guys skip over that part because you've practiced it ad nauseum at this point. Let me just tell you what our factors are going to be so we can wrap this up, okay? So spoiler alert, sorry about this. If you do the quadratic formula correctly and you reduce it correctly, you're going to end up with, what is it, -1 plus or minus root 6. Make yourself a note that that came from the quadratic formula. All right. So what? What did that tell us? What is that? Why do we need to do that? That's our last two zeros. -1 plus root 6, -1 minus root 6. Those are our last two zeros. -1 plus root 6 and -1 minus root 6. I've already gone to the trouble of graphing this thing in my calculator. I'm going to go ahead and make sure that that's right. I'll go back into here. And I don't know what's going on here, but I'm going to do second calc value again. And I'm going to try typing in -1 plus root 6. Now I know from experience, because I'm sticking a square root into this, it may do that weird thing where it says y equals 3e negative 13 or something like that, which is basically 0. So be prepared for that. Nope, nailed it. It's right at 0. So there's that one. And then that was the one with the plus. Let me try it with the minus. So second calc value, -1 minus root 6. Hoping for a 0. All right, so there's that 3e negative 11. That's basically 0, right? So we feeling good? Last thing that we got to do then, just depending on the way that the instructions go in your book, they might ask you to do a linear factorization. So in a linear factorization, all of your factors need to be linear, meaning just an x, first degree polynomials. So we're actually going to have 4 factors here, and a couple of them are going to look a little strange to you. I'm going to have x minus 3. I'm going to go ahead and write this one as 3x minus 2. And then my other 2 factors are going to come from this, and it's just x and the opposite of whatever your 0 is, right? So negative 1 plus root 6, it would be x plus 1 minus root 6, and then x plus 1 plus root 6. That would be my linear factorization. And before I call this quits, I'm going to just double check and make sure I don't need a coefficient in front of this thing. I think we're good, aren't we? We needed to have a 3x to the 4th, and I think we've got that. X, 3x, x, that would multiply. All right. When they say irreducible quadratic, what they're saying is get it down into quadratics that cannot be factored anymore. That's why we left this one here. But linear factorization is going to have 1 factor for each of your zeros. Okay, now there's a lot of stuff going on here. A lot of moving parts. I just want to take a step back and talk about like what was our process here. So what did we do first? First thing we're going to do is we're going to look at the graph. Let's see if we can look at the graph and find some information about zeros. If we get lucky, maybe we'll be able to find 1 or 2 straight from the graph. We only found 1, but we were able to use our P over Q list to come up with another one also. Once we had those 2, then we knew that we could start pulling this thing apart by using synthetic division to turn it from a 4th degree down to a depressed 2nd degree polynomial. And we can deal with 2nd degree polynomials. That's all that work that we did with quadratics. Before we end, I want to go back and talk about the first problem again, but does anybody have any questions about this whole process? So thinking back to how you dealt with these last years, does this seem more tedious or less tedious, or about the same? I feel like when I had to do this in Algebra 2 and I had to sit there and like go through this list and try thing after thing after thing, and like when you didn't get a 0 here and you're like, oh man, I gotta try another one, that was really like disheartening to me. So I kind of like this. Why not use the technology? I want to talk about this first one. How could we have gotten away without doing all this business over here? Thinking back to this, when we looked at this graph, we were able to see -3 and -1, it was bouncing. And if you remember, there was another x-intercept that was between 0 and 1. How could we have gotten this last root without doing all this mess down here? You're good. What do you think? Yeah. We could have saved ourselves a lot of work over here if we just looked at this P over Q list. So 9 would be 1, 3, and 9. See you later. Have a good day. And 5 would be 1 and 5. And what fractions can we make from that list that are between 0 and 1? Well, 1/5 and 3/5. And then we could have used our calculator to check those and just found that 3/5 worked, and we'd have been done. We wouldn't have had to go through this other stuff. Okay, I wanted to take you through the process at least twice today, so that's why we kind of took the long road, but we could have gotten there here a lot faster with the P over Q list. All right, any questions, guys? So let me tell you about Friday. There's an